When an aircraft makes contact with the runway, hundreds of tons of mass moving at high velocity transfer directly into the ground. These pavements are active structures that flex and respond to aircraft movement, managing the physical stress of every landing and takeoff. Every layer of an aerodrome pavement is engineered to absorb and dissipate kinetic energy before it can damage the underlying earth. The engineering challenge is one of prediction, determining if a specific pavement can survive the structural demand of an inbound aircraft without degrading. Solving this requires a standardized framework to translate geological data into precise operational limits. For large aircraft, visual inspections and surface-level estimations provide insufficient data for a legal safety case. Civil aviation regulations require a formalized structural calculation for any aircraft with an apron mass exceeding 5,700 kilograms. This calculation is the Aircraft Classification Rating and Pavement Classification Rating method, standardized globally as ACR PCR. To understand how this system works, we must deconstruct it from first principles, following the path of energy from the deep subgrade to the aircraft's center of gravity. This technical relationship allows aerodrome operators to make instantaneous go or no-go decisions for every inbound flight. The foundation of the system is the subgrade support strength, the elasticity of the soil beneath the runway. This data table shows the regulatory categories for elasticity. Code A represents high strength at 200 megapascals, while code D denotes ultra-low strength at 50 megapascals. Resting on this foundation is the engineered pavement structure itself, which uses two primary methods to manage weight. A code R, or rigid pavement, acts as a solid slab, spreading aircraft loads horizontally across a wide area through bending action. By contrast, a code F, or flexible pavement, uses layered aggregates to distribute stress vertically downward into the subgrade. A runway's ultimate bearing strength is the result of how its construction type distributes force into the specific elasticity of the soil. While the pavement is rated by PCR, the aircraft's demand on that pavement is quantified by its Aircraft Classification Rating, or ACR. The ACR is a mathematical expression of an aircraft's relative effect on a pavement, not just its total mass. Calculating that effect requires knowing the aircraft's center of gravity. Engineers typically use the aftmost center of gravity position, as this creates the critical loading on the main landing gear. The configuration of the gear, whether it uses dual wheels, tandem wheel setups, or tridrem laneouts, dictates how that load is dispersed before it reaches the pavement surface. The resulting ACR distills mass, gear geometry, and center of gravity into a single number representing concentrated downward force. The interface where the aircraft's force meets the pavement's architecture is the tire contact patch. Because high tire pressure can punch through a surface regardless of the total load, the system sets four pressure categories: W for unlimited, X for high, Y for medium, and Z for low. Once the subgrade, pavement type, and tire limits are known, the aerodrome establishes its official pavement classification rating. The final step is identifying the evaluation methodology used to reach that number. Code T indicates a technical evaluation based on a specific structural study. Code U means the rating is based on the historical experience of aircraft using the pavement without issue. These variables synthesize into a standardized code for global operations. This string represents a real-world reporting example: PCR 760/R/B/W/T. The code reveals the engineering. It denotes a rigid pavement, or code R, sitting on a medium-strength code B subgrade. The code T confirms a technical evaluation determined a bearing strength of 760, and code W allows for unlimited tire pressure. This leads to the operational rule. An aircraft is cleared for unrestricted use if its ACR is equal to or less than the PCR of 760. The system provides an interoperable metric for managing airport access and structural safety simultaneously. However, aircraft occasionally need to operate with an ACR that exceeds the published PCR. Pavements are resilient. They do not fail catastrophically under a single event overload. This graph shows how structural failure is measured by degradation over a specific number of repetitions, known as fatigue life. Regulations allow for occasional movements up to 10% above the reported PCR. As shown by the steeper curve, this results in accelerated fatigue. During these overload operations, engineers must monitor the pavement for specific signs of distress, such as rutting or the loss of surface microtexture. Continuous repetition of these overloads shortens the pavement's life cycle, necessitating premature and costly rehabilitation. The ACR-PCR architecture remains a vital equation for balancing the immediate needs of flight operations with the long-term viability of aviation infrastructure.